How's it going, everybody? Thanks for sticking around. 2 o'clock on Sunday. I thought it would just be Greg and I talking to ourselves in a room, which would suck because I don't even really like Greg. So today we're going to talk about a technique that you can use to decrypt information that Trojans have in their binary. I would relate the technique similar to using a calculator to solve a complex math problem. Sorry, I got a piece of coffee bean stuck in my throat. Okay, so using a calculator to solve a complex math problem kind of alleviates you the hassle of going through all the math yourself. So I know there's probably a few people out there who could tell me very quickly, or just using their head or using paper, what 46.009 divided by 8,432.007 can tell me the answer to that, but I can't. But I do know where to find my calculator. So am I screwed? No, I can still solve the problem. I can do it just as quickly. So that's what this technique is based on. We're going to use what's readily available to us to solve problems that would otherwise be a little bit difficult. So at this time, I'm going to turn it over to Greg, and he's going to take you through some intro, some theory, and then we're going to hop into a bunch of real-life demos using a few malware samples. We're going to show you some cool stuff like the disassembly rather than just boring slides. So hope you enjoy it.
Okay, so as Mike said, we're basically going to use a debugger to make... Is this better? All right, sorry about that. Okay, there we go. All right, so basically what we're going to talk about is how to use a scripting debugger to make your life easier when it comes to reversing malware. As we all know, malware basically obfuscates pretty much everything it can possibly get its hands on, like strings, configurations, protocols to communicate back to the CNC, as well as the data that it's stolen. So what we're going to do is use the functions that are already in the malware that are used for encryption and decryption against itself. And then, like Mike said, we're going to go through a couple of examples. All right, so why do malware authors obfuscate things? Well, as we all know, this is kind of a game between us as analysts and the malware authors to make our lives more difficult, to make their code more difficult to understand. Also, they've worked hard to steal the data, so they don't want other people to take their data away from them, to see what was been stolen, to make forensics more difficult. And also, they don't want people knowing what's going to and from the command and control. Like, they don't know what commands are coming down. They don't want you knowing what data is being sent back. As a result, this also makes IDS and IPS signatures and antivirus, for that matter, more difficult to write. So what we want to do is the opposite of this. We want to make the reversing easier by making it clear text. We want to know what data was stolen, what the configuration of the malware is. As also, we want to know what data is being sent to the command and control server, what instructions are being received from the command and control server. And also, we want to have a way to protect ourselves, a way to, for lack of a better solution, write signatures for IDS, IPS, and antivirus. So there are 3 basic ways you can write a decryptor for this kind of data. The first way is by far the most difficult and requires you to understand the most, which is doing it by hand. Throwing it into a disassembler or debugger, figuring out what each function does, and going that way. This approach is slow, painful, and no one likes to do it. So, and the more code you have, and the more complex that code is, the longer you're going to sit there and work on this problem. Now, recently, within the past year or so, I guess, there have been advances in decompilers that turn assembly language back into something that resembles C. So, as we all know, C is a whole hell of a lot easier to read than looking at straight assembly. But this also has its problems. It's still kind of in infancy. Things don't get typed right. You have pointers that look funny. You have data structures that just don't make any damn sense. So this isn't the all-encompassing solution. The third one, the one we're actually going to spend most of the time talking about today, is using a debugger that you can script to do all the work for you. So the malware's made the job actually easier for you. They have functions that encrypt and decrypt their data, so we can use that against it to decrypt the data. Now, depending on what you're trying to accomplish with this, not one solution is going to be the catch-all for you. If you're trying to write, a Wireshark filter, you're not going to be able to do it with a scripting debugger. You're going to need to get there, figure out what the code's doing, and write something you can compile into Wireshark. All right, so there are 3 basic classes that we came up with when it comes to doing scriptable analysis. The first one is what we call active. This is where you're not letting the malcode really do its job. You're not letting it run natively. You find the functions that do the encryption, decryption, and you attach to that. You only run that function to recover what you need. Example would be trying to recover strings, because as we all know, malware loves to obfuscate a string, so you can't see what is actually being done just by looking through a strings output. So you find the function that decrypts it for it, and then you run every string you can find through that. Another other way is called passive. This is where you more or less let the malware run as it normally would, with the exception that you're running it in a debugger at this point, and you're monitoring key aspects of it, either API calls that it does or internal functions. And we'll go through this example as well, where you're monitoring the Kraken traffic. Basically, with Kraken, it tries to encrypt. It doesn't try. It actually does encrypt the network traffic going across the wire. So what you can do is just catch it a couple of lines before, where it actually encrypts the traffic. So when it encrypts, it's going to be in plain text before it encrypts it. So you just capture that, and you can see what's going on with the network traffic. And the last one's kind of your catch-all solution when it comes to scripting. We call it recon and utility scripting. This isn't really it's kind of the kitchen sink solution, where you're looking at things like you're taking an arbitrary file, like a JPEG or PDF or whatever, and you want to see if that possibly has shellcode in it, or you want to see if there have been any shared libraries that have been hooked. Another example we have here is you can use it to unpack malware without actually running it. So what are you going to need to do this? Well, obviously you need something to work on. You need something to analyze. You can go to offensive computing and grab any number of samples. And more important than that, probably is something that scripting debugger. We're going to talk about pretty much Immunity Debugger, which has Python built into it. But you can do other things like Ollie Debug with Ollie Script. IDA has IDC as well as plugins for plugin. And it would be really helpful if you understood the concept of reverse engineering. You need to understand how to unpack things, set breakpoints, and just generally flow through a piece of code that you're reversing. Optionally, these things kind of come in handy. Some sort of disassembler to kind of IDA being the obvious choice. And unless you really enjoy infecting yourself on a routine basis, we recommend some sort of virtual environment. So at this point, I'm going to hand it over to Mike, who's going to go through several demos using real malware.
Thanks. Good job. I was just kidding about not liking Greg, by the way. Greg's awesome. Okay, so I'm going to skip this slide because it's a little boring, and we're going to go into the first disassembly. So this is a copy of the Silent Banker Trojan. And, imagine you open up this binary, you go to the strings pane, and you see a bunch of stuff that you can't read. So you're going to go to it, hop over to the first cross-reference, and find out where that string is used in the binary. Right now we can see through this little graph pane that the function is more or less pretty linear, just goes from top to bottom, doesn't do a whole lot except for several repeating actions, the first of which moves I'm going to start using this one for an example. It moves the address of this encoded string into the EAX register, and then it pushes EAX twice before calling the same function over and over again. So before even looking into this function, we can pretty much determine that this is probably the decoding function. And we also know that it takes two arguments, a pointer to an input buffer and a pointer to an output buffer, which indicates that Silent Banker in this case is going to decode the string in place. It's not going to move it to the heap or do anything like that first. So if we take a look inside this function, it begins with a loop right here. And inside the loop, it calls a function, which looks like it's got maybe some base64 derivative with a special alphabet. And it calls a few other subfunctions, and there's a bunch of stuff down here. Do we need to manually go through each of these instructions, reverse them into C, reverse them into Python in order to decrypt the same string that it's doing? No, we don't need to do that. So our technique is going to be using this small Python script right here. I hope you guys can see that. If not, it's on the CD. We're going to hard code the address of that decoding function that we saw. We're going to loop through and get each cross-reference to that function. And for each of the cross-references, we're going to disassemble backwards until we meet that move EAX, comma, offset, and then the encoded string. So we're essentially finding that move EAX instruction so that we know the address of the encoded string in memory. At that point, we're going to read the encoded address, read the string at the encoded address, so that when we spit out a table of these results, we have the encoded strings here and then the decoded strings on the right. And at that point, we're just going to jump over the encoding function, which is the equivalent of hitting F8 in Immunity Debugger or Ali Debug. So once again, we're just playing the Trojan's own internal function, using it to decrypt this information, extracting the results from it so that we have a pretty table like this. So I'm going to do a quick demo of how this is done. Can you guys see that? Yeah, should be able to see that all right. Let's do this. Okay. So we're going to just start by moving the Silent Banker DLL into Immunity Debugger. We're going to play it until the debugger's DLL loader takes us to DLL main of the Silent Banker Trojan. And then immediately, we're going to run Silent Banker _ strings at the command down there. So on disk, there's a file called Silent Banker _ strings.py, which contains the code that we just showed you on the last slide. As you can see there, the table in the middle is printing out a list of the encoded strings, and then it's printing out the corresponding decoded string. So at the beginning, these strings aren't that interesting. They're just file extensions, but that's because we're going in order. So as we move on, as you can see down in the bottom right-hand column, we're decrypting in place these strings, which now become the HTTP headers. So you can see like the content type. And here's a quick screenshot of what you might see down near the end of the strings list, showing you the exact text that the Trojan uses that might help determine what the Trojan's functionality is. So in this case, we can probably determine that it's some type of HTML injector, steals passwords, steals some type of account information from you. So the interesting thing about this method, before we get to the Q&A session and somebody runs up and says, why the hell don't you just let this Trojan run and then dump it out of memory with Lord PE or something and then run strings on that binary? There's a really good reason why we don't do that. Actually, there's two good reasons. The first one is that imagine we've got conditionals in the Trojan that only decode strings if a particular trigger is occurred. So, for example, Trojan gets a packet on port 80, decodes string A. Trojan gets a packet on port 82, decodes string B. Well, we don't really have the time to go through and find out what all those triggers are. And if we don't find out what all those triggers are, then we don't decode A and B. Okay? So the way that we're doing this is we're finding all the cross-references to the decoding function, and we're going back. So there's no way that we're going to miss anything. We don't even have to let the Trojan run in its native environment. This is an example of what Greg was talking about being active. So we're not letting the Trojan run from start to finish. We're making it run through each iteration of the call to the encoding function. So the other example that you might not get a comprehensive list of strings by just dumping it once it's running is if the Trojan does something like moving the encoded string to the heap first, decoding it there, using it, and then freeing it. In that case, if we dump it while it's running, we'll probably only get a few strings because they're being cleared every time they're being used. Whereas this case, we get them all no matter what. So the next example is also with Silent Banker. Silent Banker uses what's known as runtime dynamic linking. If you've ever analyzed malware, one of the first and easiest things to do to determine what the malware's capabilities are is by just looking at the import address table. So if it imports URL download to file, we can pretty much assume that it's going to download some file off the internet. But if we don't have that capability, it's much harder to determine what the Trojan does in more than 20 seconds. So what malware will do is use runtime dynamic linking, which consists of just calling load library on the DLL and then calling get proc address to find out the function's address of URL download to file. But the problem with that for malware authors is that the URL download to file string is still going to be compiled in the binary, and if I run strings on it, then I'm still going to find out. So just as easy as looking at the import address table. So what Silent Banker does is it uses a hash-based import address table resolver, similar to what you might see in shellcode. And what that presents is a little bit more difficult scenario for us. Here is an example of the import address resolving function. I've renamed it get proc address from hash. And as you can see, this function takes 3 arguments, the third of which is a 32-bit hash. which corresponds to a function name such as URL download to file. So that gets sent as an argument to this get proc address from hash function, which is going to go in here. It's going to begin iteration of this loop, which processes each export from the loaded DLL. And for each exported function, it's going to compute a hash using the same algorithm as that original hash was computed with. And then it's going to make a comparison. Is the hash of that function equal to what I just got passed as an argument? If it is, then I found the function that I'm trying to look up, and I'm going to save the address. EAX is being moved into ESI plus 18 hex right here. So at this point, we can determine that ESI points to the base address of the call table in memory. And what we want to do is if we follow ESI up to the beginning of the function, try to find out where that came from. ESI comes from arg0. So the base address of the call table in memory is sent as the first argument to FX table resolver. So to script around this, we want to set a breakpoint at the beginning of FX table resolver. We want to read arg0 from the stack, find out what the address in memory is. We're going to set a breakpoint at the end of this function and just play all the way through. We don't care about any of these individual instructions or any of these individual instructions. And the ability to do this is based on these, 5-6 lines of Python code, which includes the table print statement. So it's pretty easy. And what we've done now is we've got a way to, after the Silent Banker Trojan resolves all of these addresses itself, to reverse that and turn it back into something that looks like this. So instead of reading something like call dword pointer EAX plus 20 in the binary after this, you're going to be able to read EAX plus get private profile int, which makes the IDB a whole lot more readable. So this code can be reused no matter what Trojan you're dealing with. It's not limited to Silent Banker. It's just any Trojan that uses runtime dynamic linking or hash-based import address tables like this. And this is a really quick demo. We're going to start by moving the Silent Banker DLL into the debugger just like we did last time. We're going to hit play until we get to DLL main. And then right here, you can see that execution is paused at the table, the function that goes through and resolves all of those hash-based imports. So we're simply going to F8 over that until we hit the next instruction. At that point, we're going to run that API underscore resolution script, which contains those 6 lines of code that you saw on the last slide. And immediately, it's going to spit out these results right here. So the next step is simply to copy and paste this table. You can see it's got the offset on the left-hand side. And we'll just patch the IDB with that using IDA-Python, or you can use IDC or whatever. You can even do it manually if the list is small. So just a really quick 5-minute way to patch up your IDB and make it a whole lot more readable. So on to the next one is Kraken. So Kraken is a spam bot. You've probably heard of it. It's the difficulty with Kraken is that if you run a network, maybe an MSS solution, maybe you've got a lot of customers that are worried about getting infected with this, they want to block in their firewall the hosts that Kraken will try to connect to for its command and control. So how do you preemptively know what hosts that a Trojan might connect to? If it's not hard-coded as an IP address in the binary, if it's not hard-coded as a host name in the binary, and if it's not encoded in any form in the binary. In this case, Kraken has an algorithm that generates host names dynamically based on this formula. I've written the C code right here that shows you essentially what it does. There's a loop that goes through and passes this getDomain function 2 arguments, the first of which is a pointer to the output, so that's where the host name gets written. The second one is a simple integer that iterates from 0 to however many number of hosts that you want to generate. So that's how the Kraken hostname generation works. Now, for us, do we really want to let this Trojan run for potentially hours, potentially days, before we know what host names it's going to connect to? I want to know in an instant what host names this is going to connect to so that I can tell my customers, I can tell people to make sure you block so-and-so host. So let's quickly go to the Kraken example. And the way that we found this function is by getting a cross-reference to the get host by name import, which is right here. So as you can see, the first argument to that is LP hostname, which contains obviously, like moo.com or whatever. And we want to track this back and try to find out where that hostname came from. So if you go up here, it is derived from a store copy call. It's used as the destination where the EAX register contains the source. And that source is filled in after the get random hostname function is called. But obviously I've named that, so it's pretty easy to see. But before I named it, how am I supposed to determine to name this get random hostname? Well, it's because that backtracking that I just did and finding out that the EAX register at this point contains the hostname. So if you want to take a quick look at the code inside this get random hostname, there's a lot of math. There's a few conditionals, a lot of constants, a lot of multiplication, a lot of rotates, a lot of pushes. Do we need to write a formula in C or Python to mimic this function and spit out a list of host names? That might take a little bit, even if you're a really good reverse engineer. So what we did was simply looked at the input to this function. It takes two arguments, like I said before. One is the pointer to the output buffer. The other is a number, EX plus 4, which gets incremented through each iteration of the loop. So all we need to do is script around that function. We're going to replay it 1,000 times. Each time we're going to pass it a new number for that second argument, 1, 2, 3, 4, 5, and just keep going on. And then every time it's finished executing, we're just going to read the returned hostname. So we're going to do a quick demo of that. We're going to wait until the Trojan is executed in memory, starts to run. We're going to attach to it with the debugger. Type Kraken host names. And as you can see right here, it sets several breakpoints. One of them is at the very beginning of the function. It's going to reset EIP to point to that location. And it's also got a breakpoint set at the end of the function, which is right here, that return. And then it's going to hop back up. It's going to do the same thing. Do it again. And through each iteration of that, it's going to output the host name that it generates into our table. And of course, just let that run for a little bit, about 1,000 times or so. Go get lunch or something. You come back and you've got a list of all the host names that Kraken is going to connect to with its command and control protocol. Thank you. So there's also something interesting that we found during the research with Kraken, that there's a vulnerability, or not necessarily a vulnerability, but there's kind of a weakness in its cryptography model. So if you're here, you most likely know that when you're encrypting something and sending it over the network, if it's going to be secure, you don't put the encryption keys in the same message as the encrypted data. Okay? So maybe the Kraken authors didn't know that. I'm not sure. Maybe they were just lazy. But they actually decided to derive the encryption keys based on the IP address of the host machine that's infected, the CPU details, and the hard drive serial number. So it's pretty unique for each machine that it infects. But does that make it harder for us to go through an arbitrary network's packet capture and decrypt the information? No, because of the weakness. They give us all the information that we would need to decrypt the information. So based on that, this is an example of something that you can't really use the scriptable debugger method for. We wanted to write a Wireshark plugin so that network administrators could analyze their still and live network captures in order to find out when you see this UDP 447 and HTTP post traffic that Kraken generates going across the network, what's in it. And this Wireshark module that we released a few months ago can tell you that. So it parses the packet, and it extracts those keys that are in the header, and it uses those to decrypt the information. So we've got like a little tab down here that shows you what it has. It's going to be IP addresses, the spam templates, anything that the Trojan needs to do its nefarious acts. I don't have a demo for that one. Yeah, I can show that. It's not actually a demo, but it's just a packet capture, a still one, after we've installed the Kraken module. So you can click on any of the packets that Kraken generated, and you can go over to the decoded payload tab. And as you can see here, it's a list of the IP addresses that the module is going to use to connect to for its command and control. Actually, not the command and control, but for like sending spam and stuff. So that's what it looks like. I'm going on to the next demo. Lockmo is an information stealing Trojan. And there are several components to Lockmo. There's a client DLL that gets injected into windowing processes like Internet Explorer or Explorer, Firefox. And when that gets loaded by the process, it hooks multiple API functions such as PFX, import cert store, HTTP send request, so that it can snoop on the information that the process sends to that API function. So in the case of PFX import cert store, it's going to be certificates. HTTP send request is probably going to be the post payload of any logins that it's trying to make over the web. So once those API functions are triggered, the code that the Trojan inserts takes the information that it's stealing and it maps a global shared memory segment called temp_exchange, and it writes the stolen information to that shared memory segment. And then it uses send message to basically alert that remote process, which I'm going to talk about in a second, that, hey, I've stolen some information, I put it right here for you, go ahead and fetch it now. So over there in the other process, which is just a standalone executable, it has that Axel serve window loop waiting for messages from the clients. Once it gets one, it says, okay, thanks for letting me know. I'm going to map this shared memory segment now. I'm going to read what you've stolen, and I'm going to determine if there's anything that I should do with it, such as uploading it to the stolen drop site server. So this is some source code that we reversed out of the client part, the DLL. This is the code that gets executed after the trampoline hook is triggered. So traffic is redirected to, the processor is redirected to this function instead of executing the legitimate function. And as you can see, like a normal trampoline function does, it simply calls HTTP send request, the legitimate version first, and then it maps that shared memory segment, and it copies over the information that's stolen, and it uses find window. This is actually a typo. It shouldn't be __int_serve. It should be that Axel serve thing. And then it calls send message to let that remote process know that it's time to act. So if we take a look at the client DLL right here, this HTTP send request A, this is the exact same thing that I just showed you in C, but this is the disassembly version of it. You can see down here where it pushes that global temp_exchange string onto the stack, and then it calls map view of file and write, which is just an internal function that I named based on the code that happens inside of it. So we're trying to determine during execution of Internet Explorer, if somebody logs in, what exactly is this stealing? And I want to know in real time. I want to see it. I want to kind of snoop on what data it writes to the shared memory segment so that I can extract all the information and I'll have a better idea of what this Trojan is capable of doing. So can I hook map view of file in order to extract the information that I want? It seems like a likely function that we would want to hook, but in this case it's not, because at the time you hook map view of file, you haven't actually transferred over the stolen information. So it calls map view of file first, gets the address of that shared memory segment, and then it calls these two internal memcopy-like functions to transfer the data. Do we want to hook those functions? Probably not, because the address is going to be different in memory for each version of Lockmo that gets released. And we don't want to have to go through and find it every time and then hard-code it into our script. It's a little bit more work. But it's very convenient that right afterward it calls flush view of file, which doesn't actually delete the contents. It's just like flushing of contents of a file to disk. And the first parameter is the base address of the shared memory segment. So that is exactly what we want. So we'll hook that flush view of file function. We'll get access to the address of the shared memory segment, and then we can parse it and find out what information is stolen. So we're going to go to a demo. And on this workstation, I've installed Lockmo. There is another component to Lockmo that I didn't discuss there. It actually comes with a kernel rootkit also, which hides the processes and files on disk. So if that rootkit is enabled, I can't open the process that I want to debug in the debugger because the debugger can't find it. But it just so happens that Lakma comes with that kernel rootkit. It's a little bit generic. And it's kind of funny, too, because the kernel mode rootkit, you can actually disable it from user mode by simply sending a signal over the named pipe that it exposes to user mode. So that's what you're going to see us doing right here. We wrote a little program called write to landman. There's the arguments. So if we send write to landman -x, and it's going to deactivate and unhide all the items. So we'll do that. And all of a sudden, we're going to have a few new processes. See that landman work just showed up, and the kernel drv.exe down there at the bottom just showed up. So we're going to open the debugger. We're going to attach to those processes, and we're going to open up an Internet Explorer window. Go to Gmail, just some site that you can type in a username and a password. And I'm going to let this one play. We're just going to type Lakma Spy. And then we're going to go back to the Gmail window and enter our username and password and hit enter. Yeah, thanks. So this is an example of the passive method, because we're simply just letting the Trojan run from start to finish, and we're essentially just monitoring. We're not modifying the path of execution. And as you just saw, we're able to get a real-time view of all the information that it steals out of the API hooks, which includes the post-payload, your usernames and your passwords and everything. Okay, so on to the next one. Torpig, another information stealing Trojan. Just recently, well, not recently, a few 9 months maybe ago, incorporated the MBR rootkit. And the challenge to this was, this is the first one that I personally ran into that did the decryption in the kernel mode driver. So the immunity debugger is obviously a user mode debugger, which isn't going to really let you debug that kernel driver. So the kernel driver gets installed, it starts to run. The kernel component downloads a DLL and the Trojan's configuration from the web. If you're viewing it with a packet capture, you're just going to see a bunch of encrypted data. It does the decryption in kernel memory. But then the stupid thing that it does is it makes all of that decrypted content available to any user mode process through a named pipe. It's bang win money. However, you can't just connect to that named pipe and do read file, because there's an internal command and control protocol. So you need to send it the exact same sequence of bytes and the exact same value of bytes that the kernel component expects. You need to send it from user mode in order to invoke the data that you're interested in. So we wanted to write a script around the Internet Explorer process, because the DLL that Torpig downloads decrypts, and then it injects it into any process that starts. So we want to wait until Internet Explorer loads that DLL, and then we want to have a breakpoint set on create file. And we want to wait until that DLL automatically calls create file for the named pipe. And after we detect that it's opened the transmission to that named pipe, we want to set the breakpoints for read file and write file so that we can inspect the exact information that it's sending back and forth. We don't want to enable read file and write file hooks before the create file call to bang win money, because if you've ever monitored an Internet Explorer process that as it's loading into memory, it calls create file like 1,000,000 times, so that would be a whole lot of overhead. So we just want to wait until it calls create file and that bang win money, then we're going to set the read file and write file hooks. And this is the Python down here to do it. It's equally as small. There's no disassembly for this one. So the goal of this is to extract that information from the kernel which is the configuration file that Torpig downloads. It contains the list of targets that Torpig is going to try and steal information from, which is pretty essential for knowing what this Trojan is capable of doing. So we essentially just started the debugger. We began a process of Internet Explorer, and we're waiting for it to call create file on Bang Win Money. And when it does, we're going to immediately start getting some results here. So on the left-hand column, it's saying read and write, which is letting you know which of the write file and read file hooks are being activated. It's telling you the size of the information that it's reading or writing, and it's also telling you the exact data that is being sent over the pipe. So what we did in that case, taking that information, was we wrote a C program that you can run on an infected machine. And it does exactly what the Trojan does, except for, in this case, we're able to simply put the output on the screen. And so now we've got a list of all of the Trojan's targets. Even though the decryption occurs in kernel memory, even though we're not able to debug the kernel driver itself, but just by inspection of even what's happening in user mode, we're able to extract the most critical information that this Trojan is trying to hide. So that's pretty cool. So the last one is called Trojan X, encryption keygen. Can't actually tell you the name of this Trojan because, well, for various reasons, none of which we can tell you. But so this Trojan is really interesting because it's also an information stealer. And the information that it steals, it encrypts before posting to the drop site. Now, if the Trojan just generates a random encryption key and then encrypts the data with it, sends it to the drop site server, how is the attacker himself going to know what the encryption key is if it's generated randomly? He needs some way of knowing. And these guys aren't exactly as dumb as the other people, but they're pretty dumb. They didn't include the encryption keys in the same message as the encrypted data. What they did was they exploded, using arbitrary math, the 16-byte encryption key that it generates randomly into a 32-byte number, and it sends the 32-byte number along with the encrypted data. So when you recover these files on the website, you first need to extract the 32-byte number, and then you need to somehow reverse engineer that back to the 16-byte encryption key, and then you need to reverse the encryption function so that you can decrypt it. So the encryption function itself turned out to be pretty easy, and the Trojan doesn't actually have in its own binary the decryption function. It's different from the encryption function. It's not reversible. So we actually did need to do that by hand, which, like I said, wasn't too bad. But then we're still troubled by the fact that we needed to generate a 32-byte key from a 32-byte number. A 16-byte key from a 32-byte number. So let me jump over to the disassembly real quick. Here's the keygen 16 primary as I've named it. This function generates, using their custom pseudo-random number generator, a 16-byte key. Now there happens to be this particular vulnerability in the keygen that makes that pseudo-random number not so random, which, just keep that in mind for a second. After that, it sends the 16-byte primary key, which is used for encryption, to the keygen 8 secondary function, which outputs an 8-byte secondary key. And then that 8-byte secondary key is passed to this function, which generates another 8-byte key, which then gets sent to this function, which takes that 8-byte tertiary key and turns it into a 32-byte number. And if you want to just take a look at why I don't want to reverse this manually, there's a whole lot of crap in there. Okay, so that's a whole another world right there that we don't necessarily want to take the time to reverse. But are we screwed? No. So what we can do is, given that the 16-byte key is always going to be the same, I'm sorry, the 16-byte key is not always going to be the same. It's going to be generated pseudo-randomly with that vulnerability, of course. But given a particular 16-byte number, this generates the same 8-byte secondary key, this generates the same 8-byte tertiary key, and this generates the same 32-byte final key. And that's the one that's transmitted in the uploaded packet. So here's an example of one of the log files that we recovered from a rated drop site. So in yellow right there is the 32-byte key. And then in blue right after is the size of the encrypted data. And then in green is the encrypted data. So what we did was, based on that vulnerability in the keys, here's demo X, we just simply made a wrapper around these few functions. So we called keygen 16 primary. We let the Trojan run until after this reorder big num function. And at that point, we control memory. We can read whatever values we want. So we want to save the 32-byte number that it generated, and we want to associate that with the 16-byte number that was input to this entire sequence of events. And then we're going to do it again, and then we're going to do it again. And we did that 5,000 times. And I will show you how this works. Based on that vulnerability, 5,000 keys is enough to decrypt 100% of the records that we recovered from the website. So what we just did was we logged into a website with Internet Explorer while the Trojan is infected on the machine. We have a breakpoint right here at the encrypt main function, which is what I just showed you in the disassembly. The reason we did that is because there's actually a second parameter to that tertiary function besides the 8-byte secondary key, and it's a number that the Trojan downloads from the internet and decodes from a configuration file and then passes to this function. So do I need to download that configuration file and decrypt it myself and then pass it to this function? No, I'll just let the Trojan run naturally like I just did. I had a breakpoint set, I just logged into the website, and the Trojan did all of that itself once I get to this point. And then we're going to select the function here. It's going to loop through 1,000 times, or 5,000 times, and it's going to generate this binary file on disk, which contains a mapping of the 16-byte primary keys to the 32-byte final keys. And then all of those logs that we recovered from the website, we're going to process them, look for the 32-byte number, and we're going to say, hey, is this 32-byte number included in that list of 5,000 that we generated? If so, give me the corresponding 16-byte encryption key. And at that point, we've already got the decryption code written, so we'll just send it through. And like I said, that was capable of decoding 100% of the logs that we found. So that's all for the demos, and Greg's going to wrap up with some utilities and some other things that you can do that are fun using a scripted debugger.
All right. The mic here. Okay, so I mentioned earlier in the presentation about utility functions and recon functions, or scripts, sorry. One thing you can do is look for arbitrary shellcode, or shellcode arbitrary file, rather, I'm sorry. So let's say you have, a JPEG or PDF, doc file, whatever you think might have shellcode in it. Well, shellcode is going to have certain characteristics, such as it's going to jump somewhere within the memory that it has and then start executing. It's kind of a trampoline. So one thing you can do is write a quick script that starts at byte 0, disassembles the file in memory, checks to see if it's a jump or a call or whatever. But if it is, then jump to that location, see if that location is inside the memory that was loaded for the file, see if that instruction makes sense. So if you do jump within memory and you jump to like an out or an in or some other privileged instructions, odds are that what you have is just happenstance. It's curiosity. But if it does jump to a valid instruction, then the odds are you have shellcode in your file. So what that looks like, real quick. All right, so this is actually this script Mike wrote. What it did, it went through I think this was a JPEG, right? Went through a JPEG.
Oh no, wait, it was a malicious PDF, I think.
Oh, sorry, PDF. Went through a PDF, did this process. It started at the top, disassembled. If it was a jump or a call, it checked to see where it went to, and if it was within the memory range, it checked to see what instructions was next. As you can see, it'll produce a lot of data, not necessarily all of it useful. But if you look at the highlighted portion here for this demo, you can see that the jump landed within the memory range of the file that was loaded, and it looks like a valid instruction. So it's doing a move from a known NT data structure. So odds are that's your shellcode. So if you jump to that location using this script, you can disassemble it. You can see that odds are pretty good that's shellcode. So I think we also clicked on this too, right?
What's that?
This script on the disk?
Yeah. I think
So all right, we're running out of time. Is this yours?
Yeah, sure. Another cool thing you can do is, you've got access to that user mode memory. If you want to look for trampoline hooks, you can obviously do that, like with Gmer or some other rootkit detection script. But assume that you want to find out exactly what the purpose of those API hooks are. So Gmer will tell you, hey, there's an API hook on internet read file, and it jumps to 0x8D0000. But does that, really tell you what the purpose of the hook is? So with some scripts in the debugger, you can, number one, enumerate the same trampoline hooks as Gmer, and you can also set a breakpoint on the destination of the trampoline hooks, and you can just use the browser as you normally would, wait for those triggers to get hooked, and then you can debug it, find out exactly what it's doing with the parameters that get sent to internet read file. So it's pretty easy, just a normal way of detecting trampoline hooks, just looking at the prologue of the legitimate function. Does it contain a jump to some arbitrary memory and arbitrary location in memory, or does it call some arbitrary location in memory? So it's pretty easy to do that. This is an example of, I think this is Silent Banker again. As you can see over there on the opcode, that's the instruction at the prologue of those respective functions on the left-hand side. So wininet.http send request down there at the bottom would normally contain probably like a push EBP or something like that. But in this case, it contains a push of the random address, well, not random, but the address of the hook code in memory that's going to that you're going to want to follow if you're trying to debug it and find out what it does.
All right. So we're pretty much done here, but there are a few things you need to be careful of whenever you're scripting. First and foremost, as we pointed out, scripting may not actually be the best solution for you. The wire structure, for example. So know what you want to do, know what you want to accomplish, and that will tell you if you can script it or not. So if you're given to a customer, odds are you're going to have to do some manual or assisted reversing, and good luck with that. The next thing is kernel space doesn't script well. If you can try, but we highly recommend that you look at things more like in the user land, like hook certain calls to kernel space actually happen in user space. Hook those instead. And it's important to understand that you're dealing with a script here. You didn't compile this, so it's interpreted, and interpretation takes time. Some of the demos we had, like I think the Kraken domain name actually runs for quite a bit of time, so don't be surprised if your script does run for a bit.
Like we said, go to lunch.
Yeah. And finally, since you are running your malware in a debugger, it may be aware of that and may be a little pissy about that. So there are tricks, obviously, you can do to make your debugger a little less visible to the malware. So you might want to try those. So at that point, we are done. So, anything else to add?
No.